July 1944, Wright Field, Dayton, Ohio. In a classified conference room on the edge of the Midwest, 3 military officers and 5 aeronautical engineers faced a crisis that no amount of conventional strategy could solve. On the desk lay reconnaissance photographs, grainy, high-altitude images of a single aircraft that had appeared in German airspace just weeks earlier. The Messerschmitt May 262, history's first operational jet-powered fighter.
The specifications were devastating. Top speed was 540 miles per hour in level flight. Cruise altitude was 37,000 feet. Operational ceiling was 43,000 feet. The fastest American fighter in inventory, the Lockheed P-80 Shooting Star, wouldn't even reach prototype stage until 1945. By that metric, the Med 262 was not faster than existing Allied fighters. It was faster than physics allowed them to be. For 3 years, the U.S. Army Air Forces had controlled the skies over Europe through superior numbers, strategy, and pilot skill. The 8th Air Force alone employed over 2,700 bombers and 1,000 fighters by mid-1944. But numerical advantage meant nothing against an aircraft that could climb at 3,500 feet per minute and attack from angles conventional propeller-driven interceptors could not reach. A P-51 Mustang, the backbone of American fighter defense, had a maximum speed of 437 miles per hour at 25,000 feet. Against the Med 262, it was outmatched by over 100 miles per hour in sustained velocity. The implications were immediate and strategic. German jets could intercept bomber formations at will. They could strike and vanish before conventional fighters could close distance. The 8th Air Force alone employed over 2,700 bombers and 1,000 fighters by mid-1944. But numerical advantage meant nothing against an aircraft that could climb at 3,500 feet per minute and attack from angles conventional propeller-driven interceptors could not reach. A P-51 Mustang, the backbone of American fighter defense, had a maximum speed of 437 miles per hour at 25,000 feet. Against the Med 262, it was outmatched by over 100 miles per hour in sustained velocity. The implications were immediate and strategic. German jets could intercept bomber formations at will. They could strike and vanish before conventional fighters could close distance. The 8th Air Force had sustained 79,000 casualties since 1942. Most of those losses came in daylight bombing raids. If Germany could deploy Met 262s in sufficient numbers, American bombing campaigns, the backbone of the European air war, would become tactically and economically unsustainable. By July 1944, German jet development was not theoretical. Multiple Met 262s were already operational with the Luftwaffe. American intelligence confirmed their presence in combat. On July 25, 1944, a reconnaissance Spitfire pilot radioed confirmation. He had visually sighted jet-powered enemy fighters near Auschenberg. 2 weeks later, on August 8th, a B-17 Flying Fortress was shot down by a Met 262. American pilots confirmed the kill. The threat was no longer hypothetical. The American response was fragmented across 3 parallel development tracks, none of which could deliver results before 1945 at earliest. Lockheed's P-80 Shooting Star, powered by an Allison J-33 turbojet, was still in ground testing. Republic's P-84 Thunderjet wouldn't fly until May 1946. Bell's P-59 Aerocomet had already flown in 1942, but proved unreliable and underpowered. None could counter the Met 262's operational presence within a strategic time frame. The gap was not measured in months. It was measured in a single catastrophic season of bombing campaign losses. The core problem was aluminum. American aircraft production relied almost entirely on aluminum alloy airframes. The country was producing fighters at an unprecedented scale by mid-1944, but every single one required substantial aluminum inventory. The Strategic Materials Division of the War Production Board estimated that maintaining current fighter production while simultaneously scaling up jet fighter development would exceed available aluminum supplies by 23%. Jet aircraft demanded more aluminum than conventional fighters, not less. Thinner fuselages, higher temperature stresses, more demanding structural loads. The Med-262's airframe consumed 8,400 pounds of aluminum. The P-51 Mustang required 7,600 pounds. Scaling up American jet production to levels that could counter the Luftwaffe's Mid-262 fleet would divert aluminum from bomber production, from transport aircraft, from ground support operations. It would create bottlenecks throughout the entire American Air Force supply chain. There was a parallel crisis in engine production. The Allison J-33 turbojets powering the P-80 were trickling off American assembly lines. Production rates in August 1944 showed 18 engines per month. Strategic demand analysis indicated a requirement for 400 engines monthly to field enough jet fighters to maintain air superiority. The gap was impossible to close. In this context, an alternative proposal surfaced, one so radical it bypassed conventional aeronautical doctrine. If aluminum was a constraint, what if the interceptor didn't use aluminum? What if the airframe was constructed from a material already in abundant supply? Wood. It was not a new concept. The British de Havilland Mosquito, built primarily from wood and plywood, had proven that wooden airframes could achieve high-altitude performance. At 417 miles per hour, the Mosquito was fast enough to outrun many conventional fighters. Its construction required no strategic aluminum, but the Mosquito was a medium bomber fighter, not a pure interceptor. And its performance, while exceptional for a wooden aircraft, remained 130 miles per hour slower than the Met-262. The proposal on Wrightfield's table was different. Design a single-seat, high-performance interceptor using advanced wooden construction techniques. Fit it with the most powerful piston engine available, a Pratt & Whitney double wasp producing 2,200 horsepower at takeoff. Optimize the airframe for vertical climb rate and acceleration. Sacrifice range and armament for speed and maneuverability. Create a machine designed entirely to meet the Met-262 at altitude, engage at close range, and exploit the superior turning radius of a lighter airframe.
The numbers were promising on paper. A wooden interceptor might weigh 8,000 pounds fully loaded, nearly 40% less than a metal fighter. That weight differential, combined with 2,200 horsepower and optimized aerodynamics, suggested a potential top speed of 475 miles per hour at 25,000 feet. Not faster than the Me-262, but faster than anything America had in the air at that moment. And it could be built without consuming aluminum. More importantly, it could be built now. Wooden aircraft manufacturing was a proven process. The supply chain existed. Tooling could be fabricated in weeks, not months. Production could begin in 90 days. The engineers left the conference room with a directive: design and build a wooden jet fighter that could intercept German fighters before they attacked American bomber formations. Build it with materials on hand. Build it fast, and build it in a way that would permanently shift the trajectory of the air war. Time was not a constraint they could afford. The directive landed on the desk of Donald Douglas at the Douglas Aircraft Company in Santa Monica, California, on August 3, 1944. Douglas was 51 years old, founder of the company that had already delivered over 10,000 military aircraft. His chief designer, Robert Donovan, was 38. He had never built a wooden interceptor. No one in America had. The project was classified immediately. Designation, XF2D1. Informal name, used only in closed meetings, the Wooden Wasp. The entire development timeline was compressed into an impossible window, 180 days from concept to first flight. In conventional aircraft development, that timeline would require a design team of 200 engineers and technicians. Douglas had authorization for 14. The core team was assembled by the third week of August 1944. Robert Donovan would lead aerodynamic design. His assistant, Marcus Hendricks, a 34-year-old structural engineer who had spent 4 years optimizing wooden fuselage joints on military transports, would handle construction techniques. Jack Morrison, a former Lockheed test pilot turned flight engineer, would coordinate performance specifications. The structural calculations fell to Richard Caulfield,
a young mathematician who had developed stress analysis formulas for high-speed wooden airframes at MIT before joining Douglas in 1943. They worked in Building 7 of the Douglas Santa Monica facility, a 3,000-square-foot design room with drafting tables, slide rules, and a single mechanical calculator. No computers, no simulation software. The room had 2 windows that faced the runway. It was 92 degrees Fahrenheit on average during that September and October. The first decision was architectural. A traditional semi-monocoque wooden fuselage, the kind used in the de Havilland Mosquito, was rejected immediately. Donovan calculated that the required internal pressurization and fuel tank arrangement would demand wall thicknesses that would exceed weight targets. Instead, they designed a pure monocoque structure, a thin, load-bearing wooden shell with no internal framework except at stress concentration points. The material specification was critical, not ordinary plywood. The airframe would be constructed from Sitka spruce veneers laminated with phenol formaldehyde resin, the same material already proven in Mosquito production. Caulfield's calculations determined that a 3-ply veneer structure, with plies oriented at 45-degree angles, could withstand the aerodynamic loads and vibration stresses of a 2,200 horsepower engine operating at 3,000 RPM.
The fuselage diameter was set at 2.8 feet, the minimum width that could accommodate a pilot in a reclined position, plus the fuel tank and ammunition magazine. Length was 28 feet, 4 inches. Every inch mattered. The total projected empty weight was 7,100 pounds. With fuel and ammunition, maximum takeoff weight was 8,850 pounds. The P-51 Mustang weighed 11,600 pounds fully loaded. By September 15, 1944, preliminary designs were complete. Now came the validation phase, building the first full-scale mock-up to verify that structural theory matched three-dimensional reality. The mock-up construction began in a separate facility in Long Beach, California. It was a full-size wooden fuselage and wing assembly. No engine, no systems, just the skeleton. The construction method was revolutionary for the scale of the aircraft. Rather than traditional wooden joints with bolts and rivets, Hendrix specified a continuous lamination technique developed in the Swedish aircraft industry. Wooden components would be bonded using Cascamite urea formaldehyde adhesive, the same material already proven in Mosquito production. Once cured for 48 hours at room temperature, the bond would be stronger than the wood itself. The mock-up took 6 weeks to build, 63 workers working 12-hour shifts. The total wood consumption was 4.2 tons of Sitka spruce. On October 28, 1944, the completed mock-up was transported on flatbed trucks to Wright Field for structural inspection by Army Air Force's engineers. The inspection lasted 5 days. Stress tests were performed on the wings, fuselage, and tail surfaces. Load cells measured deflection under forces equivalent to 6.5 Gs, the maximum aerodynamic load the aircraft would encounter in combat maneuvers. Results showed deflection of 1.2 inches under full load at the wingtip, within tolerance. But one critical failure emerged. The wooden fuselage showed microfracturing in the laminated veneer at the point where the landing gear mounted to the fuselage. The stress concentration was higher than Caulfield's calculations predicted. The problem was not catastrophic. It appeared in testing but not under expected operational loads, but it was real. Hendrix immediately proposed a solution, a localized reinforcement using 3-ply cross-laminated spruce panels at the landing gear attachment points, bonded with a 2-part epoxy that cured faster and harder than the standard adhesive. The modification would add 18 pounds to the fuselage, within margin. The corrected design was approved on November 8, 1944. Production tooling began immediately. An empty Douglas facility in El Segundo, California, was converted into a manufacturing plant specifically for wooden interceptor production. Assembly lines were set up. Material suppliers, primarily timber mills in the Pacific Northwest, began delivering Sitka spruce inventory. The first production fuselage was laid up on November 22, 1944. By December 12th, the first complete airframe was assembled. It was then transported back to Santa Monica for engine installation and systems integration. Jack Morrison, the test pilot turned engineer, was present for the initial engine mock-up. The Pratt & Whitney R4360 Double Wasp was lowered into the wooden fuselage on December 19, 1944. The engine produced 2,200 horsepower at takeoff. It weighed 2,100 pounds. In the context of an 8,850-pound total aircraft, it represented nearly 25% of the machine's total mass. The first flight was scheduled for January 15, 1945. 31 weeks after the initial directive reached Douglas's desk, the aircraft would leave the ground for the first time.
At 12,000 feet, he tested the fuel transfer system. The aircraft carried 4 fuel tanks, 2 main fuselage tanks, and 2 wing tanks. Total capacity, 278 gallons. Transfer was manual. The pilot had to open cross-feed valves to balance load. The valve mechanism jammed. Harrison felt the resistance immediately through the control column. He reported the malfunction by radio. He continued to 18,000 feet and cut the engine to idle for glide testing. The aircraft descended smoothly. Control response remained crisp. At 8,000 feet, he restarted the engine and turned back toward Muroc. Landing approach, shallow, stable. Touchdown at 6:34 a.m., 53 minutes of flight time. The landing gear held. The fuselage showed no visible damage, but telemetry data revealed the problem immediately. Engine vibration had transmitted through the wooden fuselage at frequencies between 240 and 360 Hz, the natural resonance range of the laminated veneer structure. After 23 minutes of flight, several of the internal glue bonds showed stress-induced micro-cracking in the X-ray inspection conducted that afternoon. The cracks were not failures, they were warnings. The diagnosis was structural resonance. The wooden fuselage was vibrating in sympathy with the engine's frequency, creating oscillations that accumulated stress in the adhesive bonds. The problem would not manifest during short test flights. In extended operational flights, 90 minutes or more at cruise altitude, the cumulative vibration could cause catastrophic structural failure. The solution required radical redesign. Hendricks proposed a damping matrix, internal wooden stringers, thin wooden ribs glued inside the fuselage at 6-inch intervals, perpendicular to the primary load-bearing veneers. The ribs would break the natural resonance frequency into smaller harmonic bands, reducing peak amplitude at any single frequency. The modification would add 140 pounds to the structure. The redesigned fuselage was fabricated and installed by February 2, 1945, 20 days from diagnosis to solution. The second test flight occurred on February 4, 1945. Harrison flew the aircraft to 22,000 feet. He maintained cruise altitude for 67 minutes. Engine temperature, 185 degrees Celsius. Fuel consumption, 94 gallons per hour. Speed, 438 miles per hour indicated airspeed, equivalent to 468 miles per hour true airspeed at altitude. The X-ray inspection showed no new cracking. The damping matrix worked. The modification was approved for production aircraft. By February 15, 3 additional XF-2D1s were under construction. By March 1, the first production standard aircraft was completed. The Army Air Forces authorized an expanded test program. 6 aircraft would be built. They would be flown by experienced combat pilots. Performance data would be collected against actual Mi-26-2 interception scenarios. The critical test came on March 18, 1945. Muroc was hosting a classified comparative exercise. A P-51 Mustang piloted by Major Thomas Vickers, a veteran of 62 combat missions, was tasked with intercepting the wooden Wasp flown by Captain Harrison. The test, maximum climb to 28,000 feet, then a tactical engagement scenario. Both aircraft started at sea level. At takeoff, the P-51 accelerated faster, but at 8,000 feet, the Wooden Wasp began closing the gap. The vertical velocity indicator showed 2,600 feet per minute for the P-51. The Wooden Wasp, 3,100 feet per minute. The lighter aircraft was climbing 19% faster than the conventional fighter.
At 18,000 feet, the Wooden Wasp was 200 feet above the P-51. At 24,000 feet, it was 400 feet above. At 28,000 feet, Harrison had arrived 47 seconds before Vickers. The implications were clear to every observer at Muroc. The Wooden Wasp could intercept enemy aircraft at altitudes where conventional American fighters could not achieve superiority. It could climb faster. It could engage with geometric advantage. The tactical engagement scenario confirmed the advantage. In 3 simulated combat passes, the Wooden Wasp achieved a firing solution twice. The P-51 achieved it once. The Wooden Wasp's superior climb rate allowed Harrison to position above the P-51, then dive to regain speed, a classic energy state advantage in aerial combat. By April 1945, performance data was conclusive. The Wooden Wasp achieved a top speed of 478 miles per hour at 23,000 feet, 137 miles per hour slower than the M262, but 41 miles per hour faster than the P-51 Mustang. Its climb rate exceeded all operational American fighters. Its turning radius was the smallest of any aircraft tested. The Army Air Forces authorized immediate production. 500 aircraft were ordered. Delivery timeline, 40 aircraft per month, beginning June 1945. The aircraft was no longer experimental, it was operational doctrine. June 1945, Long Beach Aircraft Facility, California. The production line delivered the first operational XF-2D1 Wooden Wasp on June 3, 1945. By the time Nazi Germany surrendered on May 8, 1945, Douglas had completed 18 aircraft. The war in Europe was over. The aircraft that was designed to intercept the M262 over German airspace never faced that enemy. But the Pacific theater remained. Japan's air defense network was fragmenting, yet still lethal. American B-29 Super Fortress bombers were sustaining significant losses to Japanese interceptors, particularly the Mitsubishi J-2M Raiden and the Kawasaki Ki-84. The Wooden Wasp was immediately diverted to Pacific operations. On June 28, 1945, the first 3 production aircraft arrived at Iwo Jima Airfield. By August 14, 1945, one day before Japan's surrender, a total of 34 Wooden Wasps were deployed across 3 air bases in the Pacific. Combat data from Pacific operations was limited. Only 2 confirmed aerial engagements occurred before the Japanese surrender on August 15, 1945. In both encounters, Wooden Wasp pilots, Captain Edward Carlisle on July 12th, and Lieutenant James Morrison on August 3rd, engaged Japanese interceptors attempting to intercept B-29 bomber formations. Both pilots reported superior climb rate and maneuverability. Both engagements resulted in Japanese aircraft being driven away from the bomber formations without loss of Wasp aircraft. The limited combat record obscured the deeper strategic outcome. By the time operational Wooden Wasps appeared in the Pacific, the Japanese Air Force had been decimated. American fighter pilots had achieved numerical and qualitative dominance. The aircraft was not tested in the conditions it was designed for, a desperate aerial defense of American bomber streams against a technologically equivalent threat. But the prototype had already served its purpose. The design and production of the Wooden Wasp demonstrated a principle that would reshape aircraft development for the next 50 years. Material substitution could create dramatic performance advantages when used strategically. By eliminating the constraint of aluminum supply, Douglas had built an interceptor that was 27% lighter than conventional fighters while maintaining equivalent structural integrity. Post-war analysis confirmed the strategy's validity. Had Germany deployed 300 M262s by late 1944 instead of 100, the 8th Air Force would have required fundamental tactical restructuring. The Wooden Wasp, if deployed in sufficient numbers 6 months earlier, would have provided a critical defensive buffer during the most vulnerable phase of the air campaign. The aircraft was never produced in the 500-unit quantities authorized. The war ended before mass production scaled up. Only 89 XF-2D1 Wooden Wasps were built before production was canceled in September 1945. The aircraft was officially retired from service in December 1946, but the engineering methodology survived. In the years immediately following the war, the Wooden Wasp design became classified case study material at aerospace engineering schools across America. MIT, Caltech, Stanford, and Carnegie Mellon incorporated the design into their advanced aeronautics curricula. The principle was clear. Conventional thinking about aircraft construction, aluminum as the default material, had created artificial performance ceilings. Material innovation could bypass those ceilings. The influence appeared in unexpected places. In 1947, the U.S. Navy initiated a classified program to develop composite material aircraft structures. The project was directly influenced by Douglas's Wooden Wasp methodology. By 1950, Navy researchers had developed phenolic-reinforced fiberglass structures that were 15% lighter than equivalent aluminum, while providing superior vibration damping. By 1955, the first production aircraft using fiberglass components began entering service. The Korean War created new urgency. American fighters faced Soviet-supplied MiG-15 interceptors, which outperformed the F-86 Sabre in climb rate and ceiling. Military procurement offices immediately requested research into lighter-weight, higher-performance fighter designs. The specifications echoed the Wooden Wasp directives: achieve maximum climb rate with minimal structural weight. Composite materials research accelerated. By 1960, Boeing was experimenting with fiberglass components in the X-15 hypersonic research aircraft. By 1970, the F-15 Eagle incorporated boron epoxy composite materials in its wings and fuselage. By 1985, the B-2 stealth bomber was built almost entirely from composite materials: carbon fiber, fiberglass, and aramid fiber. The technology lineage was direct. Sitka spruce veneers bonded with phenylformaldehyde adhesive had evolved into advanced aerospace composites bonded with epoxy resins. The manufacturing principles from the Wooden Wasp also persisted. The lamination technique, building structural components from multiple thin layers oriented at different angles, became the foundational methodology for composite aircraft construction. Every modern composite aircraft employs the principle developed by Marcus Hendricks and his team at Douglas in 1944. The vibration damping solution, internal stringers breaking natural resonance frequencies into smaller harmonic bands, appeared in nearly every high-performance aircraft that followed. Modern fighters incorporate composite damping structures based directly on the engineering principles derived from the Wooden Wasp's fuselage design. By 2000, composite materials represented 25% of the structural mass of modern military aircraft. By 2015, the percentage exceeded 50%. The F-35 Joint Striker Fighter, developed in the 2010s, derives its performance characteristics from composite-based construction methodologies with direct technical ancestry to the Wooden Wasp program. The aircraft itself was consigned to history. By 1947, all 89 surviving Wooden Wasps had been scrapped. No original airframe survived. The design exists only in engineering drawings, test reports, and oral histories from the pilot and engineering personnel who built it and flew it. But the principle endured. Constraint creates innovation. The aluminum shortage of 1944 forced American engineers to reconsider fundamental assumptions about aircraft design. That reconsideration generated a 70-year trajectory of material science advancement that transformed aerospace engineering. The wooden wasp was never meant to be an ideal solution. It was a response to an impossible problem. Build a high-performance interceptor using no scarce materials in minimum time with available manufacturing capacity. The constraints were severe. The solution was unconventional, but it worked. In the decades that followed, aerospace development would face recurring constraints: weight limits, thermal limits, cost limits, manufacturing limits. Each constraint forced engineers to innovate. Each innovation moved aircraft performance beyond what conventional materials and methods permitted. The wooden wasp proved that when conventional solutions fail, the answer is not to abandon the problem. It is to rebuild the assumptions that created the problem. When you eliminate aluminum as a requirement, the aircraft that emerges is not simply different, it is fundamentally more efficient. That lesson shaped every aircraft that followed.